Good morning, guys. Today we will discuss graph of polynomial functions and its applications. So, first of all, let me talk about graph of general polynomial functions. So if you look at the slides, you can see that if you have a function f(x) equal to a times x to the power n, so the value of a, it determines the what? The width of the graph. If absolute value of a is greater than 1, the graph is stretched vertically, right? And the graph is narrower. And if the value of a is between, absolute value of a is between 0 and 1, the graph is vertically shrunk or make it wider. So let me give you a simple example. Like if you have a function f(x) equal to, let's say, 2x squared, right? So what is the value of a here? This is 2, right? And this is bigger than what? 1, right? So if you draw the graph of f(x) equal to x squared, you guys know that the graph of f(x) equal to x squared, it's something like this. Is that right? So let's say this is f(x) equal to x squared. And if you want to draw the graph of f(x) equal to 2x squared, so since the value of a is greater than 1 here, you see the absolute value of a is absolute value of 2, which is 2 itself, right? 2 is greater than 1, right? Absolute value of a is greater than 1. If you want to draw the graph, it will be vertically stretched. So, and it will be more narrower, something like this. So the green one is the graph of the function f(x) equal to 2x squared. Did you see that? So that is vertically stretched. Make sense? Yeah. Or you can think in this way: if the leading coefficient of, like a simple polynomial function is greater than 1, if the absolute value of leading coefficient is greater than 1, the graph will be vertically stretched, and vertically stretched means it will be more narrower than the original graph. That makes sense? Like, I can give you another example also. Let's say you guys know the graph of the absolute value function f(x) equal to absolute value of x. But in this case, it's about the polynomial. Okay, so let's say you know the graph of f(x) equal to x cubed, right? The cubic function. You guys know that, right? And then you see you have a graph like something like this. You remember that? And this is f(x) equal to x cubed. And if you have a 1 here, it will be 1, right? Right? Are you with me? So this is the point 1, 1. The graph passes through the point 1, 1, right? And if you have a, let's say, -1 here, if you have a -1 here, so it's going to be also what? -1. But this is -1, -1, okay? Right? But if you want to find out, if you want to draw the graph of f(x) equal to, let's say, 3x cubed, what will happen? So if you draw the graph of f(x) equal to 3x cubed, you see if I plug in 1, it's going to be 3. So this function, the graph of this function passes through the point what? 1, 3, right? Did you see that? If I plug in 1 here, 3 times 1 cubed is 3. So now 1, 3, 1, 3, 2, 3. So it passes through the point what? This point, right? And if we plug in negative 1, it will be negative 3. So negative 1, it will be negative 3. Negative 3 will be somewhere here. Negative 2, negative 3, negative 1, comma, negative 3, it passes through. So now you see the graph, it's look like, are you guys with me? Right. Did you see that? So the green, you see the green graph, right? This is the graph of what? Fx equal to 3x cubed. And this is vertically stretched, right, by a factor of 3. And the green graph is more narrower than the what? Black one. Make sense? Did you see what I mean? It's vertically stretched. So if you see the coefficient of x cubed here is greater than 1, right? So in that case, the graph is stretched vertically, making it narrower. Got it? Does that make sense? So so let's say instead of fx equal to 2x squared, you can draw the graph of fx equal to, let's say fx equal to 1/2 x squared. So now here the value of absolute value of a is absolute value of 1/2, right? So absolute value of 1/2 is 1/2, and this is less than what? 1. This is between 0 and 1, right? 0 is less than 1/2 is less than 1. In this case, the graph will be more what? It will be more wider, you see, so it will be something like this. The black one is the graph of the function fx equal to 1/2 x squared. That makes sense, right? So anyway, so now you see the graph is vertically compressed, or you can say vertically shrunk, more wider. So you need to know these things, okay? And then the next one is, and you guys know that, like when you have a graph of fx equal to ax raised to the power n, we want to generalize this. Like we have a 2, 3, it can be 4, 5, you know what I mean? It can be x to the power, let's say, instead of 3x cubed, you can have a 3x to the power 5, right? But if when you generalize, then you have a function fx, you have a function fx equal to ax raised to the power n. Right? So now the graph of fx equal to negative ax to the power n, this is the what? Reflection of this graph, right, across x-axis. Make sense? So that means if you want to reflect, let's say the black one is fx equal to 1/2 x squared. If you want to reflect across the x-axis, right? So the graph looks like this, you see? So if you reflect this across x-axis, this is your x-axis, this is your y-axis. You guys know that, right? So if you reflect, then you'll have what? Something like this. Make sense? And this is the graph of, let's say, you can say like fx equal to negative 1/2 x squared. Negative 1/2 x squared. See that? Reflect. So this is the what? Reflection of this graph, right? The graph of this is the reflection of fx equal to ax raised to the power n across x-axis. So are you guys with me? Right? And then if you have the graph of, let's say, fx equal to the graph of fx equal to ax to the power n plus k. This is the what? This is the vertical shift of this, the graph of this function, right? So the graph of this function is translated k units up. That makes sense? Are you with me, guys? If you translated the graph of this function, right, k unit up, if k is positive, then you will get the graph of what? This function. If k is negative, the graph of this function is obtained by shifting the graph of this function k unit down. Does that make sense? Right? So for particular example, you see, let's say you have a very simple example, okay? Like you have so this is your x-axis, this is your y-axis, and you have a graph of the function, let's say fx equal to a negative half x squared. Sorry, positive fx equal to half x squared, right? And now if you want to shift this, let's say if the value of k is 2, now the graph of gx equal to fx plus k. So this is same as gx equal to your fx is half x squared plus k. K is 2, right? So now half x squared plus 2, the graph of this is the vertical shift of this, right? By how many unit? 2 unit up. We did that last time also, if you remember. So this is you shifted this 2 unit up. So this is 1 unit, 2 unit. So it will be here, and this point will be 2 unit up. This point will be 2 unit up. So you'll have a graph like this. So this is the graph of gx equal to half x squared plus 2. That makes sense. Because the value of k is 2, positive, right? It's shifted up. And if the value of k is negative 2, so that means this is less than 0, right? So now the graph of, let's say, h of x equal to fx plus k is negative 2. So, but what is your fx? Half x squared, right? Half x squared minus 2. So that means this graph, this is fx equal to what? This is fx equal to half x squared. Is that right? So this is shifted how many unit? 2 unit down. Because value of k is negative. So now it is shifted down, guys. So this is shifted 1 unit, 2 unit. So this point is shifted here. This point is shifted here. Are you with me, guys? This point is shifted here. Is that right? You know what I mean, right? So you have something like this. It's shifted down, 2 unit down. You know what I mean? So, and then if you have if you want to compare the graph of, so let me write down here. So if you have let's say fx equal to a parenthesis x minus h to the power n, okay, right? So this is translated, if h is positive, the graph of this function, fx equal to a parenthesis x minus h to the power n, if h is positive, okay? So this, compared with this graph, with the graph of fx equal to ax to the power n, the graph of this function is shifted 8 units to the right. You see what I'm talking? So the graph of this function is translated 8 units to the right. So you can say the graph of, let me write down here, the graph of fx equal to this is translated h units to the right, because h is positive. Okay, if you want to compare with the graph of this. Okay, so don't get confused. Compared with the graph of fx equal to this. The graph of this is translated h units to the right if h is positive. So what does that mean? So that means if you have, let's say you have h equals to, let's say 2, right? So if kx equal to half x minus 2 square. So what does that mean? So that means you have the graph of half x square. This is the green one, is that right? So graph of half x square is the green one, right? So the green one is shifted how many units? 2 units to the right. To get the graph of this function, the green graph, which is the graph of this function fx equal to half x square, is shifted 2 units to the right. So this graph is shifted 2 units, 1 unit, 2 units. So at this point shifted here. You see what I'm talking, right? So you have something like this. Are you guys with me? Make sense? Yes? Huh? Did you get it? Are you guys with me? Yeah. And now if h is positive, the graph of fx equal to a parenthesis x minus h to the power n. If h is negative, is translated h units to the left. So that means, let's say your value of h is negative 2, right? So now let's say your function is Lx. So this function is half x minus negative 2, x minus negative 2 square. Are you with me, guys? Right? So this function is, this is half x negative times negative positive 2 square. Now the graph of this function is obtained by shifting the graph of fx equal to half x square. How many unit? 2 unit. In which direction? Left. Right? So this graph is shifted, like you see, the green one is the graph of fx equal to half x square. The graph of this function is obtained by shifting this graph 2 units to the left. Make sense? Okay. So now this point is shifted to 1 unit, 2 units. So it's shifted here. You see, this point is shifted 1 unit, 2 unit here, and this point is shifted 1 unit, 2 unit here. You see what I'm talking, right? You will have something like this. You see that? The black one is the graph of Lx equal to half parenthesis x plus 2 square. So this is all about. And then if you have the graph of compared with the graph of fx equal to a x raised to the power n, the graph of compared with the graph of this, right? So the graph of fx equal to a parenthesis x minus h raised to the power n plus k is the combination, so the combination of what? This translation. Like let's say if h is positive, for example, if h is positive and k is positive, what will happen? You shift this graph h units to the right and then k unit up. You see that? Are you with me? And if h is positive and k is negative, the graph of this function is obtained by shifting the graph of this function, right, h units to the right and k units down. Does that make sense? Yeah. And if, and similarly, if h is negative and k is negative, you will obtain the graph of this function by shifting the graph of this function h units left, k units down. Right? And if we do this, you will obtain the graph of this function, right, by shifting the graph of this function h unit left, k unit up. Okay? So look here. So if you look here, the graph, each polynomial function determine the largest open intervals of the domain over which its function is increasing or decreasing. Okay? So your function is f(x) equal to x to the power 5 minus 2. And the graph of this function is obtained by shifting the graph of this. So compared with the graph of what? Compared with the graph of f(x) equal to x to the power 5, the graph of f(x) equal to x to the power 5 minus 2 is vertical shift. Vertical shift of 2 units down. Is that right? That makes sense? So now the graph of f(x) equal to x to the power 5. So I believe, like you see the x to the power 3, the graph of f(x) equal to x to the power 3, x to the power 5, x to the power 7, x to the power 9, their end behavior looks same. You know what I mean? Like, you know f(x) equal to x cubed is something like this. You know that, right? This, right? So f(x) equal to x to the power 5 is pretty much the similar shape. It's pretty much the what? Similar shape. So the graph of f(x) equal to x to the power 5, it will be something like this. It's pretty much similar. You know what I mean? X square, x to the power 4, x to the power 6, x to the power. If you have even power, right? It looks parabola. If you have an odd, x cubed, x to the power 5, x to the power 7, it looks like this. So now this is shifted 2 unit down. Let's see, this is this, right? 2 unit down. So 0 unit, like 1 unit, 2 unit down. Okay, so this point is shifted here, right? Every point is shifted 2 unit down. So you'll have a graph something like this. Are you guys with me? Does that make sense? Yeah. So the real one is, this is f(x) equal to x to the power 5 minus 2. So this is the graph of this function, right? And then you have to determine the largest open interval of the domain over which the function is increasing or decreasing. So what do you think? Is the function is increasing here or decreasing here? Do you find the intervals, open intervals on the domain on which the function is decreasing? Did you see? What do you think? Is this function increasing or decreasing? You know the decreasing function, right? Increasing and decreasing function, right? So what do you think here? Is this increasing or decreasing? So this function is increasing, is that right? Throughout the domain. Does it make sense? So now you see, let's say, hey, if you have something like this, you know, if you have something like this, decreasing from negative infinity to 0, is that right? And this is what? Increasing. But here you see everywhere what? Increasing, right? So the function is increasing throughout the domain. Make sense, guys? Yes? So yeah. Did you see that? So if you look at the slides, you know, you can see the function is increasing, you know, like on its entire domain. Right? See that? Okay. So you can write the function is increasing on negative infinity, comma positive infinity. Okay? So you see fx equal to x to the power pi minus 2. The graph of this function is, you can see, this is increasing on entire domain, so that is negative infinity, comma positive infinity. So this is good, okay? So now if you look here, guys, the graph of fx equal to x to the power 6 is shifted, how many units? 1 unit. In which direction, left or right? What do you think? Yes, so you have fx equal to x plus 1 raised to the power 6. Is that right? So the graph of fx equal to x, the graph of this function, okay? The graph of fx equal to x plus 1 raised to the power 6 is, what is this? Yeah, is obtained, you can write this, is obtained by translating or by shifting, whatever, okay? By translating the graph of fx equal to x to the power 6, right? So the graph of fx equal to x plus 1 raised to the power 6 is obtained by translating the graph of fx equal to x to the power 6. How many units? 1 unit, right? 1 unit to the left. Is that right? Are you with me, guys? 1 unit. So now, if you look at the, you see, if you remember, you know, like the graph of a square function, you know, a function like x squared, fx equal to x to the power 4, x to the power 6, x to the power 8, it's pretty much similar shape, open up parabola, okay? So now, the graph of this function, it looks like, you know, so it looks like, I think it's more wider, right? So you have 1, 1, 2, 2. It's like a, it's something like this, you know what I mean? And then they shifted 1 unit to the left, so it shifted 1 unit to the left. So what you have is, if you shift 1 unit to the left, it's going to be here, right? So, oh, sorry. So you'll have something like this, guys. Does that make sense, guys? Huh? Something like this, right? And if you look here, so this point is shifted 1 unit to the left. So this point is -1. Is that right? Right? Now, can you tell me the open interval of the domain over which the function is decreasing? What is this? What happened here? Is it decreasing or increasing? What happened here? decreasing. So from it is decreasing on negative infinity all the way up to -1, right? Decreasing on negative infinity, comma -1, and it is increasing from -1 all the way up to positive infinity. So increasing on -1, comma positive infinity. Good? Did you get it? So yes. So now if you look at the slides, okay, you see this is the graph, like it looks like this. I mean, like this is more narrower, because x plus 1 to the power 6. And if you look here, you see that this function is decreasing, determine the largest open interval of the domain. Yeah, this function is decreasing on, I think like that's a typo because they ask you the open intervals of the domain, right? So you cannot include -1 in the intervals. So you have to have open intervals, so parentheses, okay? You see what I'm talking, right? So that's what I used. Okay, anyway. So it's pretty much, if you look here, so you have fx equal to, look here, okay? If x equal to x cubed, right? This is the given function. You reflect that across the x-axis, right? And then shift it 1 unit to the right, and then translate it 3 unit up. So let me say that again. Your parent graph, your original graph is what? Fx equal to x cubed, right? Reflect across the x-axis. Then you will have fx equal to -x cubed. Is that right? Right? Let me say that again, okay? You have fx equal to x cubed. So this is the graph fx equal, this is the original graph, okay? So now, so you have a function, this is the original graph, fx equal to x cubed. If you wanna draw what? Want to draw the graph of the function what? Fx equal to -2 x minus 1 cube plus 3. Is that right? So now we start here. Then reflect across x-axis. You'll get fx equal to what? -x cubed. You understand what I mean, right? So that is, look here. So let me grab some marker. Better marker. Okay. So now you see you first draw the graph of fx equal to x cubed, So fx equal to x cubed, you guys know that the graphs look like what? This. So this is the graph of fx equal to x cubed. You reflect that across x-axis, right? When you reflect across x-axis, so fx equal to -x cubed. You know what I mean? So this part will be, so it's gonna be you reflect across x-axis, right? This is your x-axis, this is your y-axis. So the graph look like, I mean, like, I'm not good at drawing, but you see what I mean, right? So this is the reflection. So the image of this part is this, right? You have this, and the image of this part is this. Does that make sense? Right? So now you got the graph of this function, okay? So you got the graph of this. The green one is fx equal to -x cubed. Then you shift how many units? 1 unit to the right. You shift 1 unit to the right. So now you'll have a graph fx equal to -x minus 1 cubed. So you shift this graph. So let me make it a little bit better. Okay, I mean, like, it looks good, but I'm not satisfied. Okay, hold on a second. Something like this. Okay, pretty much. So now you shift this, you see, so we don't need this graph. This is the original fx equal to x cube. And you shift this graph 1 unit to the right. So if you shift this 1 unit to the right, so now you'll have a, so this point is shifted 1 unit to the right, this point is shifted 1 unit. So I think you will have, right? So you'll have a, something like this. You see that? So this one is the graph of fx equal to x negative x minus 1 whole cube. Make sense? And then, so this is fx equal to negative x minus 1 whole cube. And then you shift this graph. Let me make, so you have this, something like this. And then you shift this graph, how many unit? Shift 1 unit, no, 3 unit vertically up. Shift 3 units up. This is 1 unit. So shift 3 units up. So everything will be good, what, 3 unit up. So now this point will go 3 unit up right here. This point will go 3 unit up, right? So if you shift this 3 unit up, then you will have fx equal to negative x minus 1 whole cube plus what? 3. So the graph will be, you see, you'll have something like this. Are you guys with me? Right? So you save this 3 unit up. Make sense, guys? So this is the graph of fx equal to negative x minus 1 whole cube plus 3. And then if you, so now you see the function is, you see that the function is decreasing everywhere, is that right? It is decreasing on the entire domain. It is decreasing on entire domain, negative infinity, comma positive infinity. Okay? So yeah, look at the slides. You can see the better graph, you know. Yeah, this function is decreasing. This function is decreasing on its entire domain, right? It's not increasing, it's decreasing. So I don't know why this is increasing. This is decreasing, right? Okay. So now you look at the slides, guys. You can see that. So this graph. So this is the graph of the function. You see 3 real zeros, right? 3 real zeros. What are they? Negative 2, negative 3, and positive 1. If you look at the first graph, it has 3 real zeros. You see that? The point, you know the 0, right? Look at the point of intersection of the graph and the x-axis. Okay, the x values of the point of intersection of the graph with the x-axis are the what? Zeros. So now, if you look here, this negative 3 is a 0, and this negative 2 is a 0, and positive 1 is 0. So this is for the first graph, okay? So now if you look at the second one, how many zeros here? Only 1. So 2 is a real 0, is that right? It's only 1. And if you look at the third graph, so you see negative 2 is a 0 and positive 1 is other 0, right? So how many zeros? These are 2 real zeros, is that right? So if you go to the next slides, look here. So, and these are the polynomials, you know, of even degree. So these are the polynomials of odd degree. And look at the end behavior. When you look at the graph, the end behavior of the graph is pretty much similar to the what? X cube function, cubic function. And here, if you look here, the end behavior, if you look at the second graph, it's, the end behavior is similar to what? Similar to the graph of fx equal to negative x cube. If you look at the third one, end behavior, like look here, this and this. The end behavior is similar to what? Cubic function. And then if you go to the next slide and look at the first graph. So how many zeros are there? 1, 2, 3, 4. 4 real zeros, is that right? And you see -2, -1, +1, and +2 are 4 real zeros of this function. And if you look at the end behavior of this function, it looks like what? It's similar to the square function, right? Right? You see what I mean? End behavior means, right? Like, look here. If you have look at the open upward parabola, right? It is rising to the far right, and it is also rising to the what? Far left. That makes sense. And now here, if you look at the second graph, how many zeros are there? -2, -1, and +1. Right? And so if you look at the second one, the graph crosses the x-axis at -2, 0, and the graph tosses the x-axis, right, and turns at -1, 0. The graph crosses the x-axis and change the shape. Change the shape means, you guys know that? I mean, like, you are not familiar with the concave up and the concave down. It's concave up, like to the left of +1, from 0 to 1, it looks like concave up, and it's concave down. So you change the shape at what? 1, 0. So you see, so this is what you need to know. So if the graph of the function simply crosses the x-axis, then the x value of the point of intersection is the 0 of multiplicity 1. So this is very, very important. Okay, so let me explain this here. So you have let's say you have a graph like this, right? So the graph crosses the x-axis, simply crosses the x-axis. Right? Let's say this is C1, 0, and this is C2, 0, and this is what? C3, 0. So this C1, C2, and C3, they are zeros of multiplicity 1. You remember the multiplicity of 0. So number of times 0 occurs, 0 repeats, right? So you see the simply crosses here, like this, like this, you have the cross here at C1, 0, and it's cross at C2, 0, and it simply cross here at what? C3, 0. So that means this C1, C2, and C3 are zeros of multiplicity 1. You know the multiplicity means, right? The number of times 0 occurs. This 0 occurs only once. So this is one thing. And now the next one is if the graph tosses the x-axis, or you can say the x-axis is tangent to the graph. The graph does not cross the x-axis. You just simply toss the x-axis. So that means x-axis is the what? Tangent to the graph. You see what I'm talking, right? Did you get it? So it's something like this. Let's say you have a graph, something like this. Something like this. What happened here? This is your x-axis. This is your y-axis. Is that right? So now you see the graph simply crosses the x-axis at what? C1, 0 and C2, 0. Make sense? So at that time, the C1 and C2, they are zeros of even multiplicity. So the multiplicity of C1 can be 2, 4, 6, 8, 10, and so on. And similarly, the multiplicity of C2 is also even. You know the even means, right? That makes sense? Right? Okay. So the graph is tangent to the x-axis at C1, 0, at C2, 0. The C1 and C2, they are zeros of even multiplicity. And the graph bounces and the what? Turns at the point C1 and C2. That makes sense? You see the bounce back, right? Right? Yeah. Did I make sense? Okay. So now the next one is so the next one is, guys, if you have a, let's say, graph look like this, you know, like this. You see what happened here? The graph is wiggle. Let's say this is the point C, 0. The graph is wiggle at the point what? C, 0. The graph crosses and is also the what? Tangent. That makes sense? You see, it crosses and it's also tangent. You know, like are you guys with me? Like you know, something like this. You know, let's say at 0, 0, right? What happens? The graph crosses x-axis at 0, at x equal to 0, right? And it's also what? Tangent. So it's kind of wiggle, you know what I mean? So in that case, this is a zero of even, odd multiplicity greater than 1, okay? Odd multiplicity greater than 1. So here, did you see that? You see the graph tangent and as well as what? Crosses the x-axis. So that means you can say that C is this point C is a zero of odd multiplicity greater than 1. And remember, this is greater than 1 because, remember, if the graph simply crosses the x-axis, it will be then the C1, C2, and C3, they are zeros of multiplicity 1. Is that right? Right? So if the graph is wiggle, it's tangent towards the x-axis, and it also crosses the x-axis. You know what I mean? Does that make sense? It crosses and visualize tangent. So in that case, so these zeros are the what? Zeros of multiplicity greater than 1. Now, let me give you one example. So this is the graph of the function fx equal to what? X cube. Is that right? X cube. And you can write down this as x minus 0 cube. Is that right? Right? So how many times this 0 occurs? 3 times. So this 0 is a 0 of multiplicity 3. That makes sense? You see that? How many times this 0 occurs? Look here, this is x minus 0 times x minus 0 times x minus 0. Is that right? How many times 0 repeat? 3 times. So that's why this is a 0 of multiplicity what? 3. And 3 is an odd number. Is that right? Greater than 1. That makes sense? And let me give you very simple. So this is x-axis, this is y-axis. Look here, this is the graph of the function f(x) equal to what? X squared. Is that right? 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 And the graph, you see, it tosses the what? X-axis at the point 0. Right? Or in other words, x-axis is tangent to the graph. Make sense? So in this case, look here. So what is the 0 of this function? What is the 0 of this function? 0. Is that right? And how many times 0 repeats? How many times 0 occurs? 2 times. Is that right? Right? So this 0, this is 0, 0. This 0 is the 0 of even multiplicity, which is 2. The multiplicity of 0 is 2. That makes sense? So now if you know this, hey, we can do this one, okay? Let me. Now the end behavior of the polynomial graph is determined by the dominating term. So if you look at the slides, the end behavior of a polynomial graph is determined by the dominating term, that is the term of the greatest degree. Okay? So now here, this is a polynomial function, and f(x) equal to a n x to the power n, a plus a n minus 1 x raised to the power n minus 1 plus blah 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 plus a0. Did you say that? So this a n x to the power n is the dominating term, because this is the term of greatest degree. Are you with me? Right? You understand the dominating term, right? The term of the polynomial function with greatest degree. Let me show you the example here. Look here. For this polynomial function, to look at the left, okay? The first graph is the graph of the polynomial function f(x) equal to x raised to the power 4 minus 5x squared plus 4. Is that right? So what is the dominating term? X to the power 4. Make sense? The second graph is the graph of the polynomial function negative x to the power 6 minus x to the power 5 plus 4x to the power 4 plus 2x cubed minus 5x squared minus x plus 2. So now, what is the term with the greatest degree? Negative x to the power 6. Is that right? So this is the dominating term. Right? Negative x to the power 6 is the dominating term. That makes sense? And then we talk like, you look here. So remember we talked like if the graph of the function simply crosses the x-axis, right, at c comma 0, c is a 0 of multiplicity 1. We said that, right? Right? So now look here. Look at the first graph. The graph of the function simply crosses, right? Simply crosses x-axis at what? X equal to negative 2. Is that right? So negative 2 is a 0 of multiplicity 1. So that's why you have x plus 2, just, like you have x plus 2 here. And the same thing happened. Negative 1 is a 0 of multiplicity 1. So that's why here x plus 1. Did you see that? Now look here. What about this negative 1? The graph of the function tosses the what? x-axis are at -1. Is that right? Right? Or x-axis is tangent to the graph of the function at -1. Agree? Right? So that means, what is the multiplicity of -1? Even multiplicity, right? It can be either 2 or 4 or 6, something like that, right? So now if you look here, this -1, so the factor will be x minus -1. So x plus 1. How many times x plus 1 repeats? 2. You see that? So this is 2 is a even multiplicity. And then I told you, if the graph crosses the x-axis, and you see the graph touches the x-axis, crosses the x-axis, right? It's wiggle at what? +1. So this +1 is a 0 of multiplicity, 0 of odd multiplicity. So odd means what? 3. You see x minus 1 raised to the power 3. So we have this. Now you understand the dominating term, right? The term of greatest degree is the dominating term. Now for this polynomial, so what is the dominating term? What is the term with the greatest degree? Is that 2x cubed? So if you look here, fx equal to, so you have a 2x cubed plus 8x squared plus 2x minus 12, right? So you see the dominating term is the term of greatest degree. Is that right? So if you look at the first term, it has a degree 3. Second term, it has a degree 2. 8x squared has a degree 2. 2x has a degree what? 1. -12 has degree what? 0. Is that right? So now the term of greatest degree is 2xu. So the dominating term. So the dominating term is 2x cubed. Does that make sense? Right? And now, hey, you have to look here. So this 2x cubed, if you look at the graph, you see the graph of 2x cubed is the vertical stretching, right, of the graph of fx equal to x cubed by a factor of what? 2. Is that right? So this will be the graph of 2x cubed looks like something like this. Agree? So this is the graph of what? Fx equal to 2x cubed. Now, what you need to know is, as the value of x gets larger and larger, your y value also becomes what? Larger and larger. Right? If the value of x, if the negative value of x with the, like if the value of x is very, very big negative number, your y value, your functional value is also what? It's very, very large negative number. So in that case, so what you need to know is, so it is large. If you look at the end behavior of this, it looks like. I just want to show the end behavior. You see, so this is x-axis, this is y-axis. You forget about everything here in the middle. Look at the end behavior. It looks like this and what? This. Did you see that? Are you with me? So now, what did you observe here? Wait, if you have a pretty big, large positive number, positive x values, it's blow up. Right? And if you have a very, very big negative number, it blows down. It goes to negative infinity. That makes sense? So the end behavior of this function, the behavior of this function is same as the what? Behavior of what? This function. Because this is the dominating term. You know what I mean? So let me say this function has the same behavior is what? This function. So this function is large and positive for large positive values of x, and large and negative for negative values of x with large absolute value. So that means it rises to the right, it rises to the right and falls to the left. That makes sense? So any function which has a dominating term ax to the power n, where n is odd, are you with me? And a is positive, it's a lot, like it. So it looks like this. So look at the slides, guys. So this is the graph of this function. Like if you draw the graph, so the graph of this function is, let me show here. The graph of this function is something like this. If you draw the graph, this is your x-axis, this is your y-axis, and the graph of this function is it's something like this, okay? This is your x-axis, this is your y-axis, and this point is 0, if you plug in x equal to 0, 0, negative 12, okay? So now if you look at the end behavior of this function, is similar to this, you see. It falls to the left, rise to the right. That makes sense? Okay. So, but you see, if you have a negative, let's say, if you have a function fx equal to let's say negative x cubed, a plus 2x squared, a minus x plus 2. This, right? So what is the dominating term? What is the dominating term? Exactly. Dominating term is, let's write in the function, it's fx equal to negative x cubed, And you guys know the graph of fx equal to negative x cubed. So now what you need to know is the graph of the behavior of this function is similar to what? This. As the value of x gets larger with absolute value. Okay, it's like if x approaches to positive infinity and x approaches to negative infinity, right? So the graph of the behavior of this function is dominated by what? This. So and you guys know that fx equal to negative x cubed, it is the reflection of fx equal to x cubed across x-axis. So the graph looks like. Let me write something like this. Did you see that? See that? And now, what does the end behavior look like? So you just erase this part, and you see the end behavior looks like what? This. You see that? So what happened here? Rises to the left, falls to the right. That makes sense? So this is what? Rises to the left, right? And this is what? Are you with me, guys? So this is falls to the left, falls to the left. And if you draw the graph of this function, and you see it is rises to the left and falls to the what? Right. Did you see that? So now, you gotta be a little bit careful. Now for this one, what is the dominating term? 2x cubed, is that right? And if you draw the graph of 2x cubed, it's what happened? Falls to the left, rises to the right. Is that right? And same thing happened here, you see. Rises to the right, falls to the left. So you gotta be you got to be careful here. You know what I mean? So this function, okay, has the same end behavior, as the function what? Fx equal to 2x cubed. And remember, the graph of fx equal to 2x cubed looks like this. The graph of fx equal to 2x cubed looks like this, right? What happened here? Rises to the right. What happened here? Falls to the left. And this is the exact graph of this function. You see what happened here? Falls to the left. What happened here? Rises to the right. You see that? They have the same end behavior. That makes sense? Okay. You got to be careful about that, okay? Now, this is what, like if A is positive, like let's say, if you have there's a whole bunch of things. So your dominating term, let's say your dominating term is ax to the power n. This is your dominating term, like negative x cubed. Okay. So if n is odd, so this is this is a polynomial of odd degree, right? So your dominating term is this. If I write down this function, let's say fx equal to ax to the power n, this is a what? This is a polynomial of odd degree. Okay. So in that case, the end behavior of graph is of this type, okay? So if A is positive and n is odd, so this is a polynomial of odd degree with A positive, okay? So in that case, your end behavior, remember this, okay, this. Remember this. End behavior will be, and you erase all these things, you have your end behavior will be false to the left and rise to the right. So this is your end behavior. That makes sense? Now, if A is negative, okay, so you have a dominating term ax to the power n, and fx equal to ax to the power n is a polynomial of odd degree. If A is negative, remember the graph of fx equal to negative x cubed. You see that? Fx equal to negative x cubed. What will happen? Rise to the left and falls to the right. You see that? Rise to the, this is the graph of fx equal to negative x cubed. Rises to the left, falls to the right. And value of A is negative here. What is the value of A? Negative 1. Is that right? Right? And what is the value of n? 3. This is odd with A negative. Is that right? So now in this case, your end behavior looks like rise to the left and falls to the right. Did you get it? Okay. So now the next one is let's say you have a dominating term. Your dominating term is ax to the power n, and this fx equal to ax raised to the power n is a polynomial of even degree. is a polynomial of even degree. Now in this case, if A is positive, now just think about this. You know, let's say simple polynomial function f(x) equal to x squared, right? So what is the value of A here? 1. This is positive. Are you guys with me? And this n, value of n is 2. And this is even. Is that right? So what does the graph look like? You guys know that. The graph looks like this. Open upward parabola. Is that right? So what will happen to the end behavior? It rises to the left as well as rises to the right. That makes sense? So now the end behavior in this case will be rises to the left and rises to the right. That makes sense? Now, if A is negative, just think about this. You have f(x) equal to negative x squared, okay? So your A is negative 1, which is negative, right? Your graph looks like what? Remember, f(x) equal to negative x squared is the reflection of f(x) equal to x squared across x-axis. Is that right? So now you see the graph looks like this. And now the end behavior. What do the end behavior look like? Falls to the left as well as what? Falls to the right. Because you have a open downward parabola. Right? So now your end behavior will be this. That makes sense? So if you know this, you can easily figure out, like this kind of thing. Now, hey, based on the discussion of the end behavior, match each function with its graph. So now, you look at the slides, right? So f(x) equal to x to the power 4 minus x squared plus 5x minus 4. Is that right? See that? So now, what is the dominating term?
X to the power 4.
Yes. Now, 4 is 4 even or odd? Even. And what is the value of A? 1. Yes. A is positive, right? N is even. Is that right? So this is the end behavior will be rises to the right as well as rises to the left. Does that make sense? So now, if you look here, which one has the rises to the left as well as rises to the right? C. So C. Look at the graph C. So C is the graph of the given function f(x) equal to x to the power 4 minus x squared plus 5x minus 4. Did you see that? Did you get it? Look at the next slide, okay? So look here. What is the dominating term?
Negative x to the power 6.
Yes, negative x to the power 6. What is the value of n? 6. Is this even or odd? Even, right? And what is the value of A? Negative. A is negative, right? N is even, right? So what will happen? It will be falls to the left as well as what? Falls to the right. Because this looks like a downward parabola, right? So now, if you look here, what happened here? Falls to the left, and this is also what? Falls to the right. So the graph of this function is what? A. That makes sense? So similarly, so yeah, you see graph of this function. Now look here. What is the dominating term?
3x to the power 3.
Yes. A is positive, right? And this is x cubed. 3 is what? 3 is odd. Is that right? So it will be falls to the left, rise to the right. Is that right? Falls to the left, rise to the right. This one. B. B, right? So now you see what I'm talking, right? So the B is the graph of this function, right? And now if you look here, okay. So hey guys, I don't have a time. I'm running out of the time. Okay, I'll see you later. Okay, I'm gonna stop here. Bye.